Did you know that the amount of force that somebody experiences is different if they're on the Earth compared to if they're on the Moon? So we're going to look at the different equations for field lines. So fields can be calculated using equations when an exact value is needed. So it can be calculated using a test body, which will be an object inserted into that field, whether it be gravitational, magnetic, or electrical. So in a gravitational field, this is the force per unit mass that an object would experience if placed in a gravitational field. As the distance from the source increases, the field strength decreases. So the farther away you get, the less gravity you experience. So the gravitational field is measured in newtons per kilogram, and there's a gravitational constant, 6.67 times 10 to the negative 11 newtons per meter squared per kilogram squared, and mass is the distance from the source. Mass is the mass of the source, and r is distance from the center of the source. So when we're talking about Earth, like in our example, where we're 20 kilometers above the surface of Earth, we have to add this to the radius of Earth, which is given to you in your data booklet. So let's calculate the gravitational field strength of Earth 20 kilometers above the surface of the Earth. And we're going to use this with the formula from the previous slide that's also in your data booklet. So our formula is G is equal to G m divided by r squared. And our gravitational field constant is given. Our mass of the Earth is given. And we have to take 20 kilometers, so 2,000 or 20,000 meters. And we have to add this to the radius of the Earth. So we're going to put in all our numbers. So we have 6.67 times 10 to the negative 11. And I'm really bad with the pens. I'm not going to put in the units because I'll run out of space. Multiplied by the mass of the Earth at 5.98 times 10 to the 24 kilograms. That's a 4. All divided by 20,000 plus 6.37 times 10 to the 6 meters, and then everything here will be squared. So I like to put brackets around all my numbers in the calculator so that I can just let the calculator do its job. So 10 to the power of 24 divided by 20,000 plus 6.37 times 10 to the power of 6 squared. So I end up with 9.77 newtons per kilogram. So my gravitational field strength, 20 kilometers above the surface of the Earth, is 9.77 newtons per kilogram squared. So I can also calculate the mass of an object that's been created by the field. So mass is the force of gravity on an object. So if the moon has an average radius of 1,740 kilometers and a mass of 7.35 times 10 to the 22 kilograms, we're going to calculate the gravitational field strength on the surface of the moon. So I have to do this really tiny here. So G is equal to Gm divided by r squared, which is going to be equal to 6.67 times 10 to the negative 11 multiplied by the mass of the moon, 7.35 times 10 to the 22nd, all divided by the radius squared, so 1,740,000 kilometers squared. So this gives us an answer of 1.62 newtons per kilogram. So that is the gravitational field strength of the moon. Now, what would the mass of an astronaut who weighed 100 kilograms on the moon be? So we're going to take the force is equal to mass times gravity equation. Gravitational field strength, the 100 kilograms, times 1.62 newtons per kilogram. And we get a total of 162 newtons would be the mass, would be the force of gravity on the astronaut on the moon. So we have a similar equation for electrical field strength. This is the force per unit charge on an object that the object would experience if placed in an electric field. So we have electric field strength equals the constant on the constant K, which is in your data booklet, multiplied by the charge on the source in coulombs, divided by the radius squared. So again, all these formulas and constants, including things like the mass of the Earth and the radius of the Earth, are in your data booklet. So electrons are scraped from your hair when you comb it, and your comb develops a charge of -4 microcoulombs. So find the electrical field strength 1 meter from the comb. So we're going to put in our formula. E equals KQ divided by R squared. And our constant is 8.99 times 10 to the 9th power. Our charge is going to be -4.0 times 10 to the -6 coulombs, because I have to convert the microcoulombs to a number, all divided by 1 meter squared. And this gives us a solution of 35.96 or 36 newtons per coulomb. So 36 newtons per coulomb is our answer, 36.0, for the electric field strength that we have when we combed our hair. So we can also calculate the force on an object created by an electric field, either between two charged objects. This would if just there was a charge on an object and an electrical field strength. So the formula I'm actually going to use in the next example is in your data booklet. This is looking at the charge, the force that one field will place on another if there's a charged object. So the force of the electric field is equal to the charge of the electric field multiplied by the charge on the object. So we're going to go 449,500 newtons per coulomb multiplied by 0.0200 coulombs. And we get an answer of 8.99 times 10 to the 3 newtons, or 8,990 newtons. So that is our force on a 0.2 coulomb charged object that's 20 meters away from an object that has an electrical field strength of 449,500 newtons per coulomb. So magnetic fields, moving charges can create a current of, and a current of electricity can create a magnetic field. So if we have moving charges, a magnetic field is created. We can do this with a coil of wire where one end is considered to be north and the other end is south. So as electrons move from north to south, this causes a spinning motion. And as those electrons spin and line up, a magnet is created. So here again, we have some gravitational and magnetic field strength icons. So when the Earth is a magnetic field because it's spinning on its axis, the charges are attracted to the north and the electrons are pushed out of the south. So we can induce that magnetic field by sliding a magnet in and out of a coil. So an electron can be deflected around the object using a magnetic field. And this is the basis for NASA to protect the moon base. So we can protect the moon base by deflecting currents by moving a magnet in and out of a coil of wires. I hope you enjoyed today's lesson on calculating field strength.